Every American soldier who fought from Guadalcanal to the frozen Chosin carried the same steel pot on his head, the M1 helmet, curved steel, a fiber liner, a chin strap that broke half the time. Simple, cheap, everywhere. By 1960, the Army had better materials, better manufacturing, and a far better understanding of ballistics and blast pressure than it had possessed in 1941. Several NATO allies had already begun moving toward new helmet designs. Canada was transitioning. The British were studying replacements. The Soviets had built the SSH-60, and yet the United States Army kept issuing the M1. They kept issuing it through Korea, through Vietnam, through Grenada, through 42 years of advances in materials science, aerospace engineering, and combat medicine. Again and again, they strapped the same basic steel shell onto the heads of American soldiers. The official explanation was cost, compatibility, the cold logic of an entrenched supply chain. Those answers were not wrong. They were just incomplete. Because what the Army had quietly discovered, and then spent 20 years trying to replace without success, was that the M1 was doing something no composite prototype could match. Not in a clean ballistic laboratory. In the field, in the mud, in the hands of men who used their helmets for things that appeared in no procurement document. The steel was surviving conditions that destroyed every candidate meant to replace it. That discovery did not make the budget hearings. It barely made the internal reports. And when the Army finally admitted why it had kept the M1 for so long, the answer said more about the gap between Washington and the frontline soldier than it did about metallurgy. The M1 helmet did not begin as a triumph of engineering. It began as an emergency fix for a problem the Army had ignored since the last war. In 1940, the standard American infantry helmet was the M1917A1, a design borrowed almost directly from the British Brodie helmet of 1915. Flat brim, shallow dome, pressed steel. It had performed adequately in the trenches of the Western Front, where most casualties came from above. Artillery fragments falling on men crouched in dugouts. That was the threat the 1917 model had been built to answer. But the Army that mobilized in 1940 was not going to fight from trenches. Armor had changed the battlefield. Mechanized infantry moved fast. Artillery fire came from more directions. And the Brodie's flat brim, designed to shed shrapnel raining down from above, created a wind vane effect at speed that made the helmet nearly impossible to wear in a moving vehicle or during a fast advance. Major Harold Sydenham of the Army Infantry Board began developing solutions in 1940. Under Brigadier General Courtney Hodges, the board trimmed the Brodie's brim, added a visor, and extended coverage down over the sides and back of the skull, exactly the areas the 1917 model had left exposed. The resulting prototype was the TS-3. McCord Radiator and Manufacturing Company in Detroit pressed the first examples from Hadfield manganese steel. Ballistic tests showed that the shell could resist a .45 caliber pistol ball at 800 foot per second, already exceeding the initial specification. The TS-3 was standardized on April 30th, 1941, as the helmet Steel M1. Its design specification was narrow: fragmentation, protection, not rifle-proof. The Army said so clearly, and soldiers who read the technical manuals knew it. The helmet existed to stop the threat that had killed the most men in the previous war: low-velocity shell fragments and debris. It entered production in 1941 and was being issued to soldiers before Pearl Harbor. But what no procurement document accounted for was what a soldier would actually do with the thing once he had it. The ballistic record on the M1 is better than it looks on paper, and far more complicated in ways the Army spent years studying. Battle casualty survey studies from World War II and the Korean War confirmed what the original designers had assumed. Fragmentation-type weapons were the primary wounding agent. That held true across nearly every theater of both wars, with the notable exception of certain Pacific Island campaigns, where small arms accounted for a higher proportion of hits. The M1 had been built for the right threat. On paper, it was doing its job. But the problems surfaced in the documented cases where the shell failed, and in the gap between what ballistic tests predicted and what actually happened when the helmet met combat. Post-war analysis by the United States Army Operations Research Office found that 54% of all hits on the steel shell failed to penetrate. That number sounds clean until you read what it implies. 46% did penetrate, and in the cases where the shell was defeated, the fragment still had to pass through the liner. It still had to travel through the gap between liner and skull. It still had to cover the offset distance built into the suspension system. Sometimes that was enough. The man lived. But the official record showed a penetrated helmet and a wounded soldier, not a saved life. And that distinction mattered when Washington tried to calculate what the thing was actually worth. Meanwhile, something else was happening that the ballistics engineers had not fully anticipated. Soldiers were using the M1 for things that had nothing to do with stopping bullets. They used it to dig fighting positions when they lost their entrenching tools. They used it to haul water. They heated rations in the steel shell. They pounded in tent stakes with it. The The Army Museum's own records acknowledge these uses explicitly, even noting that digging with the helmet was prohibited and universally ignored. The liner cracked under that kind of stress. The steel shell dented. But that durability was not accidental. Hadfield manganese steelwork hardens on impact. The dome pressing process concentrated that property. So the shell that came off the line was stronger than the flat disc it started as. The same characteristic that made it fragment-resistant also made it nearly indestructible under the punishment a soldier in the field considered routine. The Army had accidentally built something more useful than the specification described. By the early 1950s, the Army knew the M1's limitations in precise detail, and it was already working to replace it. What followed was more than 2 decades of failure. Beginning in 1942, almost immediately after the M1 entered service, Army researchers began testing alternative materials. A one-piece helmet was fabricated from Duran, a resin-impregnated glass fiber laminate. Aluminum nylon composites received ballistic testing. Nylon helmets were prototyped, fiberglass shells were developed and submitted for evaluation. Polycarbonate variants were examined under the Linclo project. Titanium shells were tested and rejected as too expensive for insufficient performance gain. Again and again, the results came back the same way. In ballistic tests, most composite prototypes performed comparably to the M1, or better. They were lighter. Several offered improved coverage. On the test range, they looked like the future. Then they went to the field. Duran prototypes, in the words of the official Army medical history, did not stand up well when exposed to the rigors of combat life. Fiberglass shells showed the same problem. Superior in ballistic tests, but prone to cracking and delamination under the mechanical stress of actual field use. A steel shell dropped on rock dented, a fiberglass shell fractured. The soldier could still wear the dented helmet. He could not wear the fractured one. Polycarbonate failed under solvent and chemical exposure, a disqualifying problem for men who handled fuel, cleaning agents, and ordnance in the same foxhole where they slept. Cost and supply chain were the official justifications the Pentagon offered every time a replacement was proposed and rejected. And those reasons were real. By the time Korea began, the Army had tens of millions of M1 shells in depots, with a distribution and maintenance network built around that specific form factor. Switching meant rebuilding logistics architecture during an active conflict. But the internal procurement reviews told a story the budget documents did not. Every composite candidate failed, not in the test that mattered to the procurement office, the ballistic test, but in the test that mattered to the man carrying it. What happens when you throw this down a hillside in the dark, step on it, use it as a shovel, and then need it to stop a fragment? The soldier in the field had known the answer since 1943. The Army spent 30 years running programs that confirmed it. Here is what the Army discovered, and what those budget justifications left out. The M1 was not just surviving because it was cheap and plentiful, though it was both. Research accumulated across 2 decades of failed replacement programs had produced a finding that was genuinely difficult to explain publicly. The helmet was saving lives in ways the original specification had never promised, and the procurement system could not easily quantify. The 54% defeat rate understated the helmet's value. Post-war analysis showed that in a significant number of cases where the shell was penetrated, soldiers survived anyway because the steel had decelerated the incoming debris before it entered the skull. The dome did not stop the threat, it slowed it. And the difference between a fragment traveling at its original velocity and the same projectile after defeating the Hadfield steel was, in documented cases, the difference between a scalp wound and a fatal penetration. Army medical history made this plain without dramatic language. The M1 probably prevented wounds in more than 70,000 men. The mechanism was not just outright defeat of the incoming round. It was the energy the dome absorbed even when it failed. It was the angle change, the curved surface imposed on irregular projectiles. It was the gap in the suspension system that gave the slowed debris distance to lose more velocity before it reached bone. None of this was hidden. The medical literature recorded it. But what the Army never explained publicly, because explaining it would have invited an uncomfortable follow-up question, was why, given all of that, it had spent 20 years and considerable resources trying to replace a helmet that was outperforming its own specification. The answer was simple. They could not find anything better that also survived how soldiers actually used it. Every composite program failed the field durability test. The M1 passed, without trying. The steel did not survive because it was superior ballistic engineering. It survived because Hadfield manganese steel was honest material. It dents when you hit it. It hardens when you work it. And it keeps working when everything more sophisticated around it has cracked, delaminated, or dissolved. The procurement system spent 4 decades building tests that proved the replacement was justified, and the replacement kept failing in ways the tests had not measured. The soldier in the field could have explained why he had been using his helmet as a shovel since 1942. Kevlar changed the equation. The PASGT, the Personnel Armor System for Ground Troops, was adopted in 1983, with widespread fielding through the mid-1980s. First used in combat during Grenada, the new shell was constructed from layered aramid fiber and achieved meaningful improvements in both coverage and ballistic performance. And with that, the Army's transition finally ended more than 40 years of continuous M1 issue. But the deeper lesson did not disappear. The design logic that field durability was just as operationally critical as ballistic rating became explicit in every helmet program that followed. PASGT development directly addressed the delamination and cracking problems that had killed earlier composite candidates. The lesson the M1 survival record had taught took 20 years to apply, but it was applied. Several countries continued issuing M1 shells or derived variants well beyond the American phase-out. Israel used them into the 1990s and kept modified versions in reserve inventories into the 2000s. South Korea developed the Bangtan family based on the same basic form, with older models phasing out after a newer type entered service in 2003. The pot soldiers called a soup dish, and a steel salad bowl outlasted every replacement candidate proposed before 1975. And the durability problem it posed became the engineering question that defined American helmet development for the next generation. There is a pattern in American military history that repeats so consistently it stops being a coincidence. The soldier in the field figures out what works. The institution spends a decade and a budget proving him right. Then the institution takes credit for a lesson it learned from the men it was supposed to be equipping. The M1 helmet worked not the way the engineer specified it, not the way the procurement office could defend in a budget hearing. It worked because Hadfield's steel was honest. It dented when you hit it. It hardened when you worked it. And it kept working when everything more sophisticated had cracked. A Korean War-era M1 in the collection of the Smithsonian's National Museum of American History tells the story cleanly. The helmet came from the 45th Infantry Division. It was hit by a mortar fragment in March 1953, near the eastern end of the Korean front. The fragment penetrated the shell. It penetrated the liner, but the soldier lived. The attending note described a scalp laceration, not a penetrating head injury. The helmet was turned in. The man was evacuated. The record was complete. That dented steel was the whole argument. Because the story of the M1 was never just the story of a helmet, it was the story of a battlefield truth the system kept trying to outthink. Washington saw cost, compatibility, supply chains, and specifications. The soldier saw something simpler. A steel shell that could stop fragments, slow the ones it could not stop, carry water, heat food, pound stakes, dig earth, take abuse, and still go back on his head when the shelling started again. That was why the M1 endured. Not because it was perfect, not because it was modern, but because in war, the best equipment is not always the most advanced piece on paper. Sometimes it is the thing that survives the mud, the blast, the fall, the boot, the fire, in the hands of the man who has no choice but to trust it. The M1 helmet did that for 42 years, and when the Army finally moved on, it did not truly leave the lesson behind. It carried that lesson forward into every helmet that came after. Field durability was not a secondary detail. It was survival, and the old steel pot had taught that lesson the hard way.